This topic is also the part of the previous class topic, which we are going to continue from there. Okay, so this is the next topic, where is the test coverage matrix. Okay, so test coverage matrix. What is the test coverage matrix? Basically, it's a device to measure the extent to which the set of test cases covers a particular program. Okay, when we create the basic path matrix, then basically we go for the program, that is the program graph. When we create the program graph, whether the test cases that we design from there covers what is the particular the coverage portion of those test cases in that particular graph. Okay, so that is what is important, because the objective of this particular testing is to cover more and more percentage of the actual the program. Okay, so this is determined. How do we determine that? How much a set of test cases has covered? How do we determine that? Obviously, we have to use some metrics to calculate those coverage portions, right? So it is basically from the test coverage matrix that we do. So there are certain definitions, for test coverage matrix. We will first discuss the basic definitions of the test coverage matrix. Now, when we create a flow graph, program flow graph, basic program flow graph, if the set of test cases is such that it covers every node, okay, that is there in the flow graph. Okay, if it covers every node of the flow graph, then that is, we indicate that coverage matrix by Z node. Okay, the way it is being, Z stands for the program graph and Z node indicates the node coverage. So first definition is that given a set of test cases for a program, they constitute the node coverage if, when executed on the program, every node in the program graph is traversed. Okay, so test cases are designed in such a way that when executed, those set of test cases, the every node in that particular graph, that is the program flow graph, is covered. Okay, when such coverage is there, we term it as the Z node coverage. Okay, and where Z indicates the program graph. That is the first definition, basic definition we discussed. Next is another definition is there, where instead of node we are considering that every edge of the program flow graph is covered by the set of test cases. Okay, we have designed the test cases in such a way that when executed, it leads to the coverage or traversal of every edges in the flow graph. Okay, and that is, such coverage is indicated by Z edge. Okay, the difference between Z node and Z edge is that in the latter, in the Z edge, we are assured that all outcomes of the decision making statements are executed. See, in the Z node, the nodes are traversed, but we may not have all the outcomes being executed. So when we have the test cases which actually the coverage is Z edge for those test case executions, then we ensure that all the outcomes of the decision making statements are executed. Okay, so obviously the Z edge is more wider than the Z node. Okay, the next definition is the Z chain. That is, the test cases for the program are designed in such a way that they constitute the chain coverage. Yesterday in the class we discussed about what is a chain. Okay, so here it leads to the coverage of all the chains in the particular graph. Okay, so every chain of length greater than or equal to 2 in the program graph is traversed. So test cases are designed in such a way that it leads to the execution of every, when executed in the program, on a program, it leads to the actually checking of every chain of length greater than or equal to 2. Okay, so all the chains of length greater than or equal to 2 are traversed when those test cases are executed. Okay. So this is denoted by the coverage is denoted by the G chain, as you can see. Next definition is the path. Okay. The coverage, the test cases are designed in such a way that all the path that constitute actually from the source node to the sink node. That is, the source node is the first node, sink node is the last node. Okay. So all the paths that constitute the from the source to sink node are being traversed. Okay. So test cases are designed in such a way that in the program flow graph, whichever path is available from the source to the sink node are all traversed. Okay. So that is given by the coverage matrix Z path. So here it is this traversal is denoted by the coverage of Z path. Okay. So remember that this definition indicates that all the path from source to the sink, that is the last node. So this coverage, it has a severe limitations regarding when there are some complicated loops, complex loops in the program. Okay. Now, a scientist E.F. Miller has suggested some very basic definition for the coverage matrix. Okay. So those basic definitions are provided by the Miller. They are popularly known as the Miller's definition. That is, suppose he has provided a table where he indicates with C subscript 0 indicates that every statement. Okay. So similarly C1 every DD path. Similarly C1T means every predicate outcome. What is a predicate? Predicates are nothing but the decisions. Okay. So every outcome of the decisions. The decisions may be the condition inside the loop, or it may be if then else structure. Okay, or it may be case structure, whatever it is. So any decision outcomes, the decision which makes to which edge it will follow. Okay, in a graph. So that for every predicate outcome he has indicated by the coverage matrix C1T. Okay, C2 is for every DD path plus loop coverage. C1 coverage means DD path coverage. So DD path coverage plus loop coverage indicates C2. Similarly, CD indicates the DD path coverage plus every pair of dependent DD path. So dependent DD path means when the particular variable is suppose assigned some value in one statement, and it is the predicate or the condition is actually that particular variable is used in another DD path. Okay, suppose some variable is used in one DD path, is assigned some value in one DD path, and then it is used in some other DD path. So that indicates the dependent DD path. So like C1 coverage plus every pair of dependent DD path indicates CD. Okay. So CMCC indicates the multiple condition coverage. Okay. So when there are multiple conditions in the predicate or the decisions. Okay. So those multiple condition coverage, means suppose one relational operators you have used some greater than less than equal to for checking one condition, then you have used and another condition. So you are basically combining two, right? And final outcome depends on the conditions you check for each of those terms, right? So that is the multiple condition coverage. So in the multiple condition coverage is indicated by the coverage matrix CMCC. Similarly, CIK is basically when there are every program path that contains up to k repetitions of the loop. Usually k is greater than, so it is basically path checking from the source to the sink node. Okay, So every program outcome that actually that contains up to k repetitions of a loop, and that is indicated by CIK. So C state is statistically significant fraction of paths. So statistically significant fraction of paths means those paths which he indicates as statistically significant, those paths are being checked for this in this coverage matrix this state. And C infinite is all possible execution paths. So entire possible execution path indicated by the C infinite. So according to these definitions, we are going to define the next terms here. So statement testing is basically statement coverage is generally viewed as the bare minimum for the coverage matrix. That is, if some statements are not executed, then obviously there is a severe gap in the set of test cases. Okay, every statement in the program flow graph has to be tested. Okay, now although the statement coverage is less than actually less adequate than the decision to decision path coverage, but still it is one of the most widely used test coverage metrics. Okay, and it is indicated by C0. Okay, that is the first test coverage by the Miller. Then DD path testing. DD path testing means that every DD path is traversed. Okay, so that is indicated by Miller. Miller has termed that as C1 metric. Okay, that is every DD path in the traversal, that is you from the basic flow graph of the program, you derive the DD path, that is the DD path graph. Okay, so from there you indicate by every DD path you try to that particular coverage, you identify whether all the DD paths have been covered by the set of test case that has been generated. Okay, so when you know that that every outcome, predicate outcome has been executed, actually this amounts to traversing every edge in the DD path graph. So we know that the predicate means the decisions, right? So if we know that every outcome of those decisions are being tested, then we know that every DD path has been covered by the set of test cases. So basically it is the testing of every outcome of the DD path. Okay, DD path graph. So C1 matrix is basically exactly same as the Z-chain definition that we have given earlier. So the C1 matrix here, the DD path testing, is nothing different from the definition that we discussed earlier just in the previous topic, that is the Z-chain. Okay, so for every if then and if then else statement, this also indicates that we have checked every true and false branches in the decision making statements like if then or if then else. Okay, and this is equivalent to the GH test graph that we have defined earlier. That is, so this means that if then and if then else, all the true side and the false side of the if then and if then else statements are being checked. That is the DD path testing. Okay, for case statement, each clause is being covered. For case statements, for those case values, case 1, case 2, case 3, that way, every clause is being checked. That also indicates that DD path testing. Okay. Another definition is simple loop coverage. Okay, which is indicated by Miller by the matrix C2. Okay, C2 means the DD path plus the loop coverage. Okay, so it is so simple view of loop testing is that every loop indicates obviously involves some decisions, some predicates, right? The condition has to be checked in the loop for its continuous execution, right? So, and we know that we need to test both outcome of the decision, one to traverse the loop, another to go out of the loop, right? So whenever there is a predicate there, that is a decision to be tested. So we know that one outcome will be to continue evaluating the loop, another outcome to go out of the loop, right? So this is actually equivalent to GH test coverage. Okay, in the earlier definition that GH we have defined earlier is the same as that one. C2 is nothing but actually the DD path coverage plus the loop. Okay, loop testing. Another is the predicate outcome testing. So every outcome, the decision predicate must be exercised. So that is the predicate outcome testing. Okay. Then dependent pairs of DD path. I told you what is the dependent pair of DD path. That is when we define reference relationship in which a variable is defined in one DD path and a reference in another DD path. Okay. So if we define the variable or assign some values to the variable in one DD path and we actually use or reference that particular variable in some other DD path, then that DD path, the next DD path as actually can be termed as those two DD path can be termed as the dependent pairs. Okay, so basically this is another way, that is the one important part of this dependency is that they are closely related to the problem of infeasible path. That is, we define that we have in a white box testing, one of the most biggest problem is the problem of infeasible path, right? When a test set of test inputs does not actually lead to actual coverage of the does not lead to the testing of that particular path, then it is the infeasible paths. So when the importance of these dependencies is that they are closely related to the problem of infeasible paths. So obviously infeasible paths actually arise from the dependencies of this DD path. Okay. So another is complex loop coverage. Miller has given it by CIK actually, which extends the loop coverage matrix to include the full path from the source to the sink. Okay. So those coverages where the test cases are such that it actually leads to the testing of all the coverages from source of the path which goes from source to the sink nodes. Okay, and basically it leads to the execution of the or checking of the complex loops. Okay, so loops testing has been studied extensively for good reasons, because loops are the highly foul-prone portions of the source code. Remember that testing of the loop is one of the most important part of the white box testing mechanism, because the loops are the portions actually which normally leads to the faults in a program. Okay, so path coverage is basically covers most of the complex loops which can be actually located in a program. Okay, so there can be three different kinds of loop coverage here. One can be termed as the concatenated loops, or simply the sequence of disjoint loops. So sequence of disjoint loop, when there is a small loop that in sequence, one loop goes as the, say, from one loop, then you go to the another loop. The other loop, there are a number of small loops which are in sequence. Then we can call as the concatenated loops. Okay. So where we have the sequence of disjoint loops, while nested loops are actually such that one loop is contained inside the another loop. Then we call it as the nested loop, right? Also, there can be another kind of loop which can be termed as the knotted loop, and one scientist called Bezier actually termed them as the horrible loop. Okay, so these loops cannot occur when the structured program concepts are followed. In structured programming, we do not have such knotted or the horrible loops. Okay, but they can occur in some languages like Java, where we have with the try and catch conditions, exception conditions, try catch parts. Okay, so there we can have such knot loops. Okay, basically when it is possible, those loops that is from outside, actually it can the loops condition can jump into the main loop. That is, when it's possible to branch into the middle of the loop. Okay, or middle of the loop, and these branches are internal to the other loops. Okay. So when you jump from outside to the middle of some loops, the main loops or internal loops, then such conditions can occur. So that is called as the Bézier's knotted loops. Okay. This will be clear from the diagram that we have here in the next slide. These are the three different loops that we are considering. That is for the testing conditions, the concatenated, nested, and the knotted. The first one is concatenated, where you have small simple loops followed by another in sequence. They are called as the concatenated loops. Okay. These are the nested loops where you have an inner loop executing between an outer loop. Okay. So both these loop conditions can arise in the structured programming languages. Okay. But in some programming languages like Java, where we have the provision of widely testing the exception conditions with try catch statements, etc. There you can have the third kind of, which is a knotted loop. Okay. So you can check, you can see this is the main loop executing here, going out from outside it has jumped into this loop. Okay. So in such conditions we call it as the horrible loop or the knotted loop. So these testing conditions are necessary to be covered by the test coverage, because loops are the most, as I told you, are the main conditions or the predicates where the fouls can arise in the program. Okay. So loop checking is one of the very important part of the test coverage. Multiple condition coverage is Miller's multiple condition coverage matrix is like, testing the decisions. Okay. When we have a multiple conditions to be evaluated or which are concatenated in the decision or in the predicate, then we need to, instead of, in certain cases we can have the total, either we can evaluate it as the true or false. Okay. So, but here we can have the entire set of individual conditions which are being joined with some and or conditions can be actually, we can create a truth table of those conditions, and we can have for every entry of the truth table we can have a test case, or for every possible or the legal version of the truth table entries we can have actually, we can create a decision table and I can create the test cases. Okay. So here that is the multiple condition coverage, that is when matrix addresses the questions of testing the decisions made by compound conditions. Okay. So instead of simply traversing such predicates as either only true and false for the entire compound conditions, we should actually investigate different ways that each outcome can occur. Okay. So we can have all the possible different ways the outcome can occur, and we should check every outcome there. Okay. So that is one possibility is to make the decision table and compound conditions of three simple conditions. We'll have 8 rules, right? 3 means 2 to the power 3, so there are 8 rules for 3 simple conditions. So yielding 8 test cases. Okay. Or another possibility is that the program compound predicates into nested simple if then else logic, which will result in the more DD path to cover. So instead of, another possibility is that let us change the compound condition to some set of nested if then else structure, and that will result in the DD path coverage. Okay. So this is indicated by Miller by the C subscript MC. Okay, that is the multiple condition coverage. Now one example from the Tangle problem, that we know in the Tangle problem that if one side is smaller than the sum of other two sides in the triangle, then the triangle can be created, right? If this condition is false, it is not possible to create the triangle. That is, one side is greater than equal to the sum of other two sides means the triangle cannot be created. So all the 3 conditions must be true. That is, A is less than B plus C, B is less than A plus C, C is less than A plus B. So all these 3 conditions. So this is a compound condition. In totality, it is a compound condition. That is, the C less than B plus C, B less than A plus C, and C less than A plus B is jointly checked by connecting through AND, right? So this is a compound condition. So instead of this checking it entirety by the compound conditions, we can actually convert it to a decision table to check the throw the multiple conditions. That is, the decision table is something like, you have 8 entries here. So when all the 3 entries are true, 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 that results in the true. That is the where it can be created. The triangle is possible to create a triangle. Otherwise, in all other cases, it is not possible to create a triangle. So these are all F. Okay, outcome are all F. Now, this is the truth table. Now, from this truth table, you can create the decision table. Okay, in a decision table, you have the condition 1, the first condition. That is, all the individual conditions, multiple conditions are checked separately. So all the individual conditions are listed here. So you have 8 different cases as per the truth table. So 2 possible outcomes. Okay, A1, A2. A1 is impossible, A2 is valid test cases. Okay, so we are considering any of the 2 conditions false, means totality 2 conditions are false is the impossible condition. We are not considering that. Okay, if only 1 condition is true, rest 2 are false, then we are not considering that in the test case. We are not generating test cases for that. So that is the impossibility condition. Okay, or all the false. Okay, so only for the other 3 conditions apart from this is obvious. These 3 conditions also we are generating the test cases and we are checking. Okay, so that is the CMCC way of checking all the conditions. So here you can see these are the test cases that get generated, and we are putting test case numbers 1, 2, 3, 4. So we are putting the values. So these are the legal values, most obvious values where the triangles can be created. So we are putting those values actually randomly. So possible cases of the first test cases where all the 3 cases are true. So 3, 4, 5, and it gives the expected output is true. Okay. For other 3, the expected output is actually false, because this condition is C greater than equal to A plus B is true. Okay. So when we have C, we have put the value C as the one of the large value which is greater than A plus B, 3 plus 4. Okay. So this condition must be false for the triangle to be true, right? For triangle to be created. So it is the 3, 4, and 9 which indicates the that 3 plus 4 is 7 and it's less than 9. So the triangle cannot be created. So this condition is true, means the expected output is false, right? That is in the test case number 2. In the previous graph or previous table, you can see that is this condition 2, test case number 2, right? This is false, this one, because in the next in the test case we have written as C greater than A equal to A plus B. Here it is true, this condition, that condition in the test case is true, right? That is why the outcome is false. But here this is true means this is the false means this is the test case number 2, right? This is false means C is greater than equal to A plus B. So for this case we are generating a test case to check the values. Okay. Similarly, for 3 and 4 also, we are generating a test case where 3 is 9, we are putting 9 for B, okay, a large value which is greater than 3 plus 4, the next 2, and we are checking with the test case, that's the test case number 3. And for the 4th, test case number 4, it is A, we are putting A as the large value. Similarly, we can have the test case generated for checking C equal to A plus B, B equal to A plus C, and A equal to B plus C also. Okay. So it is possible to generate the test to have a test case generated for this. So Miller's-Covers matrix also includes 2 other parts. One is C state, another is C infinite. So C state means that is actually constitutes statistically significant set of full program path. Okay. And all possible coverage matrix is basically that is all possible path metrics are being to have the coverage matrix. If our program covers all those Miller's coverage matrix, then obviously our program is foolproof. Okay. So thank you. This is all about the test coverage matrix. Okay. So in the next class we will continue another topic in this in connection with the path matrix only. that we'll continue in the next.